We are the UCL Computer Science Team 25, working on the virtual therapy application. Our team consists of Raresh Dolga, team leader and back and front end developer, Fazan Hassan, head of research, tester and back end developer, and Kevin Black, audio and visual lead, researcher and documentation and report editor. We are creating the virtual therapy application working in collaboration with Microsoft and Mark Pollock. In the UK, approximately 40,000 individuals are struggling with paralysis. Our project plans to aid their rehabilitation using 3D audio feedback technology, allowing patients to seek treatment even for extreme cases, such as those where they also suffer from visual impairment. The problem is that there are currently no methods for creating therapy sessions with feedback given by a computer. Presently, a therapist needs to support the sessions, but he cannot provide the feeling of how a visually impaired patient's joints are aligned. We needed to develop an application capable of analysing the user's pose and then produce a response that would help a paralysed person correct their posture during exercise sessions. The key features are that we had to capture the user's joint positions in real time and reconstruct the skeleton on the computer. Additionally, several pose detection algorithms had to be created to analyse the user's skeleton. These algorithms also had to be capable of processing data in real time. We also had to create a response in the form of 3D sound representing feedback on the user's pose. A voice command menu was also required. This was to allow blind people to interact with the application. The system was divided into multiple components. The first part is represented by sensor integration and modelling the input data from them. Next, we have the therapy module. This consists of pose analysis algorithms and creation of 3D audio feedback based on the algorithm's output. The server connection component sends information and handles the responses from the server in the application. Also, the server component represents a bridge between our software and the database, used to store different postures. We selected the Microsoft Kinect to gather information about joint position in space. The Kinect output is connected to the Unity game engine, in which we reconstruct the skeleton in an avatar form. This tool was also used for creating the augmented reality part of the application, which concerns the 3D audio effect. The algorithms that work on the input were implemented in C#. For speech recognition, we used Microsoft Speech Runtime API, and the server was constructed using Node.js and deployed on Azure. The database was MongoDB. The UI is specially designed for visually impaired users, containing vocal instructions and commands for navigation. In order to extend the possible number of users, we worked on the visual aspect as well and added buttons and a visual interface.
Hello, welcome to the main menu. Please select one of the options. To begin, say Start. To save a pose, say Register Pose or Save Pose. To reply the instructions, say Repeat or Again. Calibrate to set the environment. Exit or stop to quit the program.
Save pose.
Pose saved into the database.
Repeat.
Hello, welcome to the main menu. Please select one of the options. To begin, say Start. To save a pose, say Register Pose or Save Pose. To reply the instructions, say Repeat or Again. Calibrate to set the environment. Exit or stop to quit the program.
Calibrate.
This sound should come from the right ear. Please flip the headphones if not.
Start.
Please raise your right hand to choose the user.
Main menu.
Hello, welcome to the main menu. Please select one
Exit.
of the options.
Multiple users in front of the Kinect could interfere with our sensor, so to decide who to track, we require the user to make a special gesture. To avoid a long learning period that would be necessary to learn the specific sounds associated with each joint, we introduce keywords at the beginning of each sound script. If the user's pose changes while these keywords are said, the current phases stop, and the new keyword that maps the posture starts. This will now be a demonstration of the application in use.
Please raise your right hand to choose the user. Left hip. Your pose is correct. Left hip. Your pose is correct. Right hip. Your pose is left. Your pose right hip. Your pose is correct. Left hip. Your pose mid back front. Your pose mid back. Your pose is correct. Mid back backwards. Mid back front. Your pose is correct. Right knee. Right knee. Your pose is correct. Left knee. Your pose is correct. Right knee. Left knee. Left hip. Your pose is correct. Right knee. Left hip. Left knee. Your pose is correct. Left knee. Right hip. Your pose is correct.
Main.
Our application tracks the human skeleton in real time. We also tackled an open research problem, the human pose estimation, and managed to solve a smaller subset of the problem with our rule-based algorithms. An immersive experience was achieved by creating 3D audio feedback. Speech recognition was successfully integrated along with a database that stores poses necessary for the algorithms. Finally, a database connection was ensured by the server we constructed.